Today, I will present a specific instrument called Lidar. It's a very innovative instrument. It's also called optical radar, and you will discover later why it's called like that. I will take the opportunity of presenting these instruments and talking a little bit about the physics of the atmosphere and Arctic. That instrument is very useful because, as you know, it's quite difficult to make measurement from polar region, and so we need instruments that can allow to access remotely measurements in different regions, and that type of instrument is very useful for that purpose. So myself, I'm today here on my office. I'm part of a laboratory called LATMOS, specialized on the atmosphere. I am myself, at the beginning, specialized on optics, and you will see that Lidar is full of optics and is based with a laser. And now I became the director of this laboratory, and so I'm very glad to make this presentation today. So I will move on the outline. And as I said, before talking about the Lidar, I need to talk about the atmosphere and how in the past we investigate atmosphere and how we came to know a little bit more about the atmosphere. So I'll talk about the composition of the atmosphere and also what is light and what is a Lidar and how it's working. Okay, so directly move to the past. Of course, today we have a lot of technology with the telephone, with this type of instrument. And so it's difficult to remember how some time ago researchers were able to learn a little bit about our environment. And that was not so easy. And so I put two pictures which illustrate quite a bit how we make such investigations. We used to climb into the highest mountain to be able to penetrate into the atmosphere. That was the easiest method at that time. And so all the expeditions bring with them a lot of instrumentations and researchers to make measurements. One of the biggest discovery that was confirmed later on was that the temperature is decreasing with the altitude. So it's colder and colder, and it's why you have snow on the mountain. It's not just because it is higher and so colder than the other part of the region. Of course, I talk about Mont Blanc, one of the highest mountains in Europe, shared by France and Italy. But of course, if you want to go higher, you have this Himalaya or Andean mountain in South America, going up to 8 kilometers. So that was quite easy to investigate the first 8 kilometers. Just to give you one idea, the altitude where plane flying corresponds to something like 10, 11 kilometers. So you see that this is the main regions where we investigate at the beginning, where there is a lot of issue around the meteorology. And so then, as you see on the bottom, the first explorer make observatory at different place at high altitude to understand how atmosphere involved. So the second step was to use balloon. And so how balloon is working? At the beginning, balloon are working because we put some hot air with a fire, as you see on the, maybe I can show you, maybe you can see here the balloon. So it was brother Montgolfier, and you see there is a fire going into, so with hot air going into the balloon. And so and maybe I can make an arrow like that, you see. And so with that hot air is lighter than cold air. So then it's going up. To figure out and to understand that, you can try to remember when you see any chimney, you will see the smoke. The smoke always go up because it's warm. So warm air going up, okay? And so we make a different type of balloon to investigate the atmosphere. So of course, the first investigations also in the atmosphere with such balloon, we have also researchers, physicists that climb into the balloon to make measurements. And because it go colder and colder, some of them have trouble because sometimes it's very cold, and so some get murdered because of these expeditions. Then we were using different types of balloon, but then we replace hot air because one of the problems with the hot air is that when the balloon goes up, air, of course, became cold, and so the balloon fall down. And so later on, we discovered that some gas, and I will come back later on that gas, some gas are also like warm air, are lighter than air, and so allow to get up. This was mainly the, now it's used, the helium is used. And so, of course, it was used during war also to get up and observe the position, the military position. Now, it is still used, and you have what we call meteorological balloon. At different places around the world, and it was a very, very important network. People launch balloon with this type of instrumentations, measuring mainly this small part, measure temperature and humidity, so for the meteorology. So this was sent every day at noon, everywhere in the world, and this was the data that we inject into our model to make the forecast. Because of course, to forecast the weather, you don't need just the ground measurements. You also need to understand the whole atmosphere, because air is not just circulate horizontally, they're also going up and down. So you really need to investigate above. Then we had another instrument, which is here, the white box, that is the ozone measurements. So maybe some of you heard about the ozone hole. Of course, now we talk about climate change, but you have to remember that there was in the past, a few tens decades, an issue with ozone, and so we're measuring everywhere also with such a balloon ozone. So those balloons going up to 30 kilometers, they can carry something like between 2 and 3 kilos and not more. So when we want to investigate more the stratosphere is this layer really above 10, 20 kilometers up to 50 kilometers high. So remember, Himalaya is 8 kilometers, so we are far away from that altitude, where ozone is located. This gas protects us against UV radiations. And to study the ozone hole and the problem and the issue with ozone, we use very, very large balloon that can carry up to a few tons. So tons is like a car, you see. So we can carry a lot of instrumentations up to the stratosphere. So you see the size. This is not the biggest balloon, but you see the size with this body. This engineer, we are working on the instrument, so you can see the difference compared to the meteorological balloon. So this was a technology that was used. And then finally, we have this development of the V2, which were used during the war. And so that technology was used after the war in different countries for making meteorological rockets. So those rockets corresponds to something like 3 meters high, and are really rockets that can go up to 100 kilometers. So that was the first time we can measure 100 kilometers, and this happened during the I would say competitions to the conquest of space, and so we have to learn a little bit about the high atmosphere. We want to put satellites, so we need to know a little bit what we cross, and nobody knows. Remember, balloons goes up to 30 kilometers, and so that type of instruments, like balloon, go at the apogee, and then the payload, the instruments, fall with a parachute. Maybe we can come back on that picture, and you see clearly here in red the parachute. And so when the balloon blows at 30 kilometers, the instrument fall below a parachute and slowly get down, take measurements, and send to the ground informations by radio, and so you can get the measurements. Of course, at the beginning, there was no radio, so you have to follow by eyes your payload and got it and get the measurements. Okay, so that was the one of the. Today it was still sometimes used for research, but less and less because it's very expensive to use that type of device to study the atmosphere. So now let's talk a little bit about the atmosphere. When you live on Earth at ground level, you don't see anything. So you breathe. Of course, you all know that we need air, we need oxygen. You feel that when you go on the top of the mountain, it's less easy to breathe. So it's very clear that you need this oxygen. But also a good way to see that air is not nothing is that when you see a balloon like this one, and so of course there if you push on the balloon, you feel that there is something. So air is not nothing, you feel it. Another way to do that is to play with that type of syringe, and so if you close the one side and you push here, you feel that you push something. There is not nothing. So it's a quite of demonstrations that air is something. So what is air? It's molecules. So maybe it's something you don't know very well yet. Those are very, very small particles. Those are the basic elements that are used to compose any things around us. You all know that it can be solid, like tables and so on. It can be liquid, like water, but it can be gas. This is the three phase you can find, and of course around us there is this air full of molecules, including oxygen that we are using every day. Okay, so that's just a few elements to talk about those. But also sometimes, and you see that it's very comfortable, you have dust particles. And so if you make a zoom, you have particles of 1 micron, which is an agglomerate of different type of molecules, bigger than molecules. And of course, those particles are very nocive, but compose also part of the atmosphere. Next. One other component, in addition to molecules and particles, you have water. Water in the form of gas, but also a lot of water in gas, but we don't see it. What we see with clouds is that there is a droplet, those small droplets that compose the atmosphere. And so where is coming those droplets? When the sun hits the sea, it warms, and so there is water going up and making clouds. Okay, this is also when you cook, you see this water vapor going up, and again it's going up back because it is warm. So if you get up in the atmosphere, okay, going up in the atmosphere, the temperature, as I said before, is decreasing. So temperature is very cold, and at some point, the water in form of liquid became solid, and you see the different shape of the crystal. So the very high cloud called cirrus, like this one. At the top there is also cirrus. Like what also the contrail from airplane. All those are composed by crystal. Okay, this form of crystal is very well known because it corresponds to the snow, but there is different form of crystal that compose the atmosphere and clouds. So if I make the different compositions, you will find very small particles you cannot see that are calling molecules, bigger particles that are or dust, solid particle but very small, and also waters on the form of droplet or crystal. Okay, now before I will talk about the LiDAR, I have to talk about the nature of light, because we are using a lot of instruments based on the optics and on light. And you will see, I have to tell you, even if, of course, you are not still specialized on the physics and optics, that researchers use two types of representation of the light. It can be particles, okay, like maybe you heard about the electron. So here we call a photon. When we collect light with a detector, we need to have this view of particles, so we call photon. But also, light can be considered like a wave with different wavelengths. That waves characterize the energy of the photon, and we can see it. This representation is also used when we are talking about light, and you will see that this is most of the time what you are really feeling when we talk about the light. So let me go on the next. Maybe it's a little bit complex, but you will understand. As I said, light is an oscillations wave, and the visible, it can be visible. So this is part of the light which is visible, and the oscillations correspond to the color. So you can have UV, all the spectrum, and red. But of course, light is not only there are some waves that are not visible. You already heard about ultraviolet. You cannot see them, but on the beach with a lot of ultraviolet, you may have damage on your skin. And also there is infrared. For example, infrared is what you have on your television's remote command. And you don't see the light, but this is the light that allows to run your televisions. If you look about the spectrum of the sun, so all the color of the sun, you have this type of spectrum, and you see a lot of light coming from the visible, but also a lot of light coming from infrared. You don't see, but that are here. The UV part of the sun, you don't see it at ground level because it is absorbed by ozone. And again, it's why I told you before that it was an issue with ozone because it stopped the ultraviolet. Okay? Okay, this is maybe a little bit theoric, but if you go on the practical, I'm sure that you all already see this night feature in the atmosphere. Where it come from? These night features coming from droplet. So it's occur when just after rain. Just after rain, you still have some droplet that remain on the atmosphere and make this nice halo with the different colors of the light spectrum. You see from red to ultraviolet. Okay, and so it's not exactly the same, but you can a little bit understood what's happened if you look about the effect of the prism. If you put some light on the white light on the prism, you get the spectrum because the different wavelengths do not travel exactly the same on the prism and give you this spectrum. And this can occur at any time on your daily life. Each time you have glass, bottles, whatever, you can have this such a figure of the spectrum of the sun. Okay, so I now talk about scattering, molecular scattering. Scattering is also a very good representation to the fact that there is molecule in the atmosphere or particles. When there is light that is going up through a big lamp, you see them. Why you see them? It's just because molecules and particles are scattering in all the directions. Sorry, it's not very visible, but you can see better here. Here again, sun is sending light through trees that mask some of the part and allow some parts to get in, and you really can see the light. Why you can see the light? It's just because there is here some molecules and particles in the air that allow to scatter light in all the directions. Okay, so like my balloon I showed you previously, this is also a demonstration that air is not empty, it's full of something, and one of the big parts which include in the atmosphere are the molecules and particles. Okay, don't be afraid, I put some formula, but this is the only one, and just to show that we can observe that, but also we know the physics, we understood the physics, thanks to Lord Rayleigh, which was a researcher working on the interactions between light and different medium, understood and make the models about the scattering by molecules. And the efficiency of the scattering, it demonstrates that the efficiency of the scattering is depend of the wavelength. What is the wavelength? As I said previously, let me come back. This is the oscillation. Okay, and same here. Short oscillations for UV, larger oscillation for red light. And so, when the wavelength is large, because the efficiency is the inverse with the power 4 of the wavelength, when light is red, the efficiency is very bad. When light is blue, so shorter wavelength, efficiency is better. And so suddenly you can understood why light that is scattered on the molecules on the atmosphere is scattered very more efficiency in blue than in red. Red is not efficient, blue is very efficient. And so the light coming from the sun is suddenly blue and not red, because red is not efficiently scattered. This is what Lord Rayleigh really found and made. And so it is very, very interesting, because this explains why the sky is blue. And then why clouds are white. As I said, clouds are formed by droplets. Droplets are bigger than molecules, much more bigger. And because they are much more bigger, the efficiency of scattering is the same in red and same in blue. So that means when we look about clouds, we see the light of the sun, white, like usual. Okay? Now, when the sun, during sunset and sunrise, we still have blue sky here. But there is also very nice red. It's just because in that part, the sun is very low in the horizon, and so it is all the blue is absorbed. So even if red is not very efficient, there are only the red that remains. So we see the red. Okay, but just due to during the sunset and sunrise. Okay, so you see there is no magic in the color of the sky. Whatever we see in the sky, the interaction of light with the sky allow us to understand what is the composition, including that type of effect, the effect of the droplet in the atmosphere. If you get up in the atmosphere, in space, and you see, and you look about our atmosphere, what you clearly see is the blue sky, but it is limited. Why it is limited? Because it is limited at the part where we have molecules. Above, there is no molecules. You have to understand that the gravity on Earth, you feel the gravity every day. It's why you stay on the surface of our Earth. But the same for our atmosphere. Our atmosphere is attracted by the Earth and remain around the Earth. But as soon as you get up, of course, you have less and less atmosphere, and you can really see it when you're above. Light of the sun, it's black because it's empty. As I said, we demonstrate that air is not empty at ground. It allows us to breathe the air and the oxygen. But above, in the on space, there is no more atmosphere, no more molecules. It's why astronauts need a bottle of air to be able to get up. Even still, the people, the alpinists that get up to the Himalaya, they need air, and so they bring air with them. Okay. So let's move with some other photos, just to maybe prove or reinforce that idea. Look, this nice picture on the desert. If you hear what you see, you clearly see the blue sky. Okay, you see a moon white because all the light from the sun, you see them. You don't see all the light of the sun here, only the blue one, which are efficiently scattered by the atmosphere. If you again go on space, you see that atmosphere is not here. but is located here, okay, where you see the blue sky. And if you go to the moon, you don't see any blue sky, just because there is no atmosphere. So light, you see the sun directly on your eyes, but the light of the sun do not interact with the atmosphere because there is no molecule. Okay? So now I give you some basic principle of the atmosphere. I give you basic principle of the optics, and so I will tell you about the Lidar. So first, I want to show you a little bit about the design of a Lidar, and the principle is based on what I explained, mainly the scattering of the light. And we will show you later on a small film that allows maybe to better understand this instrument that seems to be complex, but in fact it's quite very simple instruments based on the physics. For that, we use a laser, and we use a laser to send a beam vertically, and I will explain later why we are using a laser. We have what we call a beam expander. In fact, it's optics that allow to have the right geometry of the light. Then what's happened here, as I said, light which is emitted is scattered everywhere in the sky. It is why, again, remember, it is why you see laser. If somebody has a laser on the dark, you can follow the photon because it is scattered. So we have here a big collector, a big telescope, to collect not all, but a small part of the light that's coming from molecules. Of course, we need optical filtering to remove some light that is not useful for measurements. And we convert photons, as I said. Photons are the name we give to the small particles that corresponds to the light. Okay, sorry, up. And so those photons are being collected by a detector and then convert into electric transducer and convert into a beam that can be recorded. So this is a basic principle. Maybe here is a better view, not a schematic of how it looks like. So again, the laser here, okay. The optics, kind of a small telescope, and you see the light is well focused because it is a laser. Then our telescope that collects the light, and this is a concave telescope. That means that light is then converged to a secondary mirror and then into the detector, and then this is electronic. So if you just close to the Lidar, this is what you see. This picture is obtained in south of France, in our observatory called Observatoire de Haute-Provence, and you can really see the light going up in the sky. Okay, maybe now it is time for me to show you a small movie. There will be some noise. It's not the video that has any problems. It's just because the laser makes some noise when they are working. Just because I will come back later on this. On the picture here and here, you see a continuous beam. But in fact, I said that in the introduction, I will come back later. It is a pulse laser and not a continuous. But your eyes cannot see the pulse because of the speed of the light, which is very high. And it's like a movie. It's a succession of photos, but you don't see each photo. Your eyes has a memory, and so it's a kind of a flow, and you see people moving. But in fact, it's cinema is just the picture are just following different picture, and because of your eyes, you see it moving. So it's the same for the laser. You have different pulse, but of course you cannot see those pulses. They are too quick for your eyes. So maybe let me show you some of the measurements we made at the observatory of Optical. So I don't know if you heard, but you see the laser. And so this is a high beam going to a mirror and then going up. So you clearly see the beam on the sky, and then we have telescopes that collect the light. Of course, during daytime, you cannot see the beam. It's still green. And this is the detector. Okay, and of course, we get the information on the computer in real time. We can see the number of photons we collect. That is converted, and I will tell you a little bit later on geophysics measurements, interesting for climate research and meteorology. Okay, so let's come back to the presentations. You see the different elements. So now I have to talk about few devices that is important. To make a collimated beam, of course, we used to do that in the past with the light. You see clearly how it works also for the cars. What we do, we have a light here that emits in all the directions, okay? And because of this reflector, all the light is sent on the same directions. It's not perfect, as you see. There is still a certain divergence, but this was quite a useful tool at the beginning to send the light on one direction. Let me talk a bit about the light. How it works. Light, if you put some current into a filament, it puts some energy, and so molecules get the energy. But they don't stay with the energy. Very quickly, molecules lose their energy naturally. And so when they lose the energy, they emit a photon. Okay, and it is the way it works, or with electricity, or with combustion. With combustion is the same. There is combustion, there is the emission, so excitations of the molecules that desexcite and emit a photon. The properties of that effect, which is a natural effect you all observe, is that there is many colors, many directions, because you see it in different directions, and it's a kind of a random process. And so it's why you have all the colors, all the directions. You all feel that, so I will not comment that, but you all, depending of the type of the lamps, you can have different type of the spectrum, but it's still always a large spectrum of light. Let me now talk about one specific instrument, which is a laser, and I will try to explain mainly basically how it works. The laser, you have two mirrors and a medium here we call medium of amplifications. That medium, we put some energy. Sometimes it's light, like here, but sometimes it can be discharge. Whatever we do, we put excitation on that medium. And so because it is in the cavity, and the cavity is closed at some time and open at the right time, we generate, instead of having a random effect of desexcitations, we use a process which is called simulated, because one photon will desexcite molecules and so. And then we have an avalanche effect that's allow to have a very focused beam, okay, on one color. So that's the properties. If you do a random desexcitations, you can have any colors, any reaction. If you stimulate, you can have, which was the goal of the laser, you can have a very focused beam and on one color. Okay, so this is the principle of the laser, and for the LiDAR, we can use such a system. This was used at the beginning, but very quickly we moved to the laser because it's a very well adapted lamp for our purpose, because it's one direction and one color. And so for the physics, it's very more simple to have one wavelength than having a full spectrum like the sun, and we cannot separate the different wavelengths because they all act differently on the atmosphere. Okay, so this is the explanation why we are using a laser. Now, let me explain the basic principle. Maybe I have to move first on that one. The basic principle is based on the radar. We send a pulse and we measure the time it took to the pulse to come back. Here is two illustrations of that radar. You now all know that type of radar on the road. So we send a pulse, the pulse is sent, and we measure the time the pulse returns. And so we measure the right position of the car. If you do this 2 times, then we can measure the speed of the car. This is same for some different animals. There are different of them. They're all using the same. They make a noise, and this noise propagates, and when they hit something, it comes back, and the time measure, you know, what is the distance. This is what you do on the mountain, and you feel the echo. If you cry, then you send the echo, and the time between the echo depends of the mountain all around you. Okay, this is also the same type of things you can do when you send something on a big hole, and you hear when it's fall, and the time it's fall down give you the idea that, okay, it's very far or it's very close. Okay, so this for the LiDAR is really the same. Let me go to the schematic. Don't be afraid. It's not so complicated. We put altitude and time. So we send a pulse at the beginning, and the pulse propagates in the atmosphere. Suddenly, it hits large particles. This can be a cloud, okay? And so light is scattered everywhere. But a part is scattered to the Earth, and this is what we collect. So the time it took, we collect the light, correspond to 2 times the distance to get to the cloud. And so here is what we see as a signal. We see from the time we send the pulse, we see an echo that corresponds to the distance. So the distance here is here converted by a factor of 2 to get up and down on your signal. Of course, some light can go through the cloud and maybe found another cloud here. And so again, light is going everywhere, but also on the direction of our telescope. And so we can find a second layer. So you see that this instrument is very useful to see the different layer in the atmosphere. And you have a background on the signal, which is here, that corresponds to the molecular scattering. And as I said, there is a lot of molecules close to the ground. And if you get up, there is less and less molecules. So the signal decreases very rapidly. Okay. So here you can see that with that scattering, you can see Rayleigh scattering corresponding to the molecules. And what we call me scattering, me was the name of a researcher that make also a lot of studies on the interactions of particles with light. You see clearly the different structure and the size of the cloud. So that was one of the main applications of this LiDAR. Let me show you a very old measurement. So it's not good because it's just a copy of what we get at that time. At that time, data were not archived into a computer. We only have print, okay, on a print. And so here you see clearly this axe was converted in altitude from 11 to 25 kilometers, okay? And you see clearly the signal decreasing because of the molecular decrease in the atmosphere, okay? And here we clearly see the peak, okay? Which correspond to a volcanic eruption called El Chichon. Okay, let's move. So you have the basic principle. This is all the applications. We can be on the airplane. We can be on the space shuttle. We can be from the ground. So this instrument can be used in different ways. One of the first instruments in space called ALISA. It was on the Mir, which turned around the Earth. And so the instrument was located here and provide such measurements. So you see the ground, you see the Andes, you see Cirrus, you see all the different. Of course, the power of the laser was not very much, and so data was not good at that time. So I want to move on the instrument that is today around Earth. That is called Calipso. This instrument is here with a laser that get down and make measurements and go around the Earth and can really provide a lot of information. This was sent in 2006 and still running. Of course, you see here it's a picture, an artistic picture, because you see the beam, and you should not see the beam because, as I said, on the space you cannot have any scatter, so you cannot see the beam. Okay. So now Calipso, as I said, again, the instrument, just to show you some of the measurements. When Calipso pass above our observatory in south of France, we get such a measurement. So you see nice cirrus cloud around 10 kilometers. And with Calipso, we see clearly the same. And so here in that picture, you see the path of Calipso that make that can travel all around the world because of this orbit around the world and make measurements, and it's look like this. So you can really see the structure of the cloud. Now I'm just going to the end. just to tell you that there is many applications, many told about aerosol and cloud, but with the same basic principle. You can measure temperature, ozone, water vapor, wind, and of course, the priority we had on space was for clouds and aerosol, because there is no other way to locate cloud and aerosol. And next, we will have a mission by ESA called ADM-Aeolus, which will focus on wind, because also from space, we don't have any measurements of wind. And my last slide was about, just to illustrate how it can be very useful, such an instrument. You will all hear about this Icelandic volcanoes that bring material ash, volcanic ash, up to the upper atmosphere. And because we don't know where those small particles were, it stopped the traffic. And so you can see with Calipso, we clearly see where is the volcanic plume. And so on the future, such instrument on the ground, on space, could allow really to monitor such a type of events, but of course, much more event for ozone, temperature, and so on and so on. So I'm arrived at the end. I hope you understood a bit this instrument and the application we will have on the future with just type of instrument. Thanks very much for your attention. And so maybe now we can move on the questions. If you have some of the things you don't understood or you want having more explanations.